This is a Math 3 Unit 4 review. Number 1, we are asked to multiply and simplify these two rational expressions. Factoring is key when you're multiplying or dividing these expressions. So we're first going to consider anything we can factor. So the x squared minus 9x plus 2, we're looking for two numbers that multiply to 2 and add to negative 9. And actually that doesn't factor, but looking at the worksheet, for some reason the 20 didn't print out good for me. You should have 20 in front of you. So two numbers that multiply to positive 20 and add to negative 9 should be negative. So this is going to factor to x minus 4 and x minus 5. Also, right below it, the x squared minus 4x minus 5, we're looking for two numbers that multiply to negative 5 and add to negative 4. And our two numbers are going to be negative 5 and 1. So this is going to factor to x minus 5, x plus 1. When you multiply two fractions together, you're just multiplying everything together in the numerator with stuff in the numerator and multiplying everything in the denominator with things in the denominator. We're not going to multiply anything out. We're just going to put the factors right next to each other. So x plus 1 times x minus 4 times x minus 5 all over x minus 4 times x minus 5 times x plus 1. Well, x plus 1 divided by x plus 1 is 1. X minus 4 divided by x minus 4 is 1. And x minus 5 divided by x minus 5 is also 1. And so everything canceled out, and so this is just equal to 1. Number 2. So number 2, when you divide two fractions, you end up multiplying the first fraction by the reciprocal of the second fraction. And so I'm going to write that. I'm going to rewrite the first fraction just like it is. So 20x y to the third over 14x to the fifth times, so I'm changing division to multiplication and flipping over the second fraction, which is the reciprocal. So 6x to the fourth y squared over 10x to the third power. From here, we can multiply things together, or we can reduce, however we want to do that. I'm going to reduce each fraction first and then multiply. It gives me smaller numbers to work with. 20 and 14, we can divide both of those by 2 and get 10 over 7. We have an x over x to the power of 5. We subtract the exponents. We take 1 away from the 5 and you get 4. And y to the third. So the first fraction simplified to that. The second fraction, you can divide both 6 and 10 by 2 and get 3 over 5. X to the fourth divided by x to the third. You subtract the 4 and the 3, you get x to the power of 1. We typically don't write that 1. And y squared. Now I'm going to multiply those two fractions together. You multiply the numerator times the numerator and get 30x y to the fifth power. I'm adding the 3 and the 2 together, those exponents. And then 7 times 5 is 35, x to the fourth. And then check if we can reduce even further. I can divide both 30 and 35 by 5 and get 6 over 7. I can divide x and x, or simplify the x and x to the fourth, divide them both by x, and you're left with an x to the third in the denominator and a y to the fifth in the numerator. And that's our answer. Number 3, we need to subtract two fractions. When you subtract fractions, you must have a common denominator. We already have 21 and 7, so I'm going to multiply the 7 times 3, and I have to be consistent and multiply the numerator by 3 as well. I also want an x cubed, so I'm going to multiply by x, because x squared times x is x cubed. So 3 times 4 is, we have 12x over 21x cubed minus 3 over 21x cubed. When you're subtracting and you have a common denominator, you only subtract the numerators. So 12x minus 3 over 21x to the third. Check to see if you can factor anything. In this case, we can factor a 3 from the numerator. And then see if you can divide numerator and denominator by a common factor. In this case, we can divide by 3, and we're left with 4x minus 1 over 7x to the third power. Number 4, we want to add the two fractions. You can add two fractions if the denominator is the same. Well, x minus 5 and 5 minus x are not the same, but they're very close to being the same. There's a trick, and this is, if you have 5 minus x, that's equal to negative x minus 5. And if you have a hard time seeing why, if I distribute that negative to the x and to the negative 5, I get negative x plus 5 and negative x plus 5. If I switch things around and put the positive 5 first, the negative x second, we get 5 minus x. So we are going to change our 5 minus x to negative x minus 5. So rewriting this, the first fraction I'm going to leave the same, 5x plus 1 over x minus 5, plus 16 over negative x minus 5. Now still the denominators don't look the same, but the difference is a factor of a negative 1. So we have two choices here. First, we can multiply the left side by negative 1 to match it, or we can get rid of that negative sign on the right side somehow. And here's what I'm going to do. I'm going to multiply the right-hand side by negative 1. So multiply the bottom by negative 1 and the top by negative 1. So what happens is I get 5x plus 1 over x minus 5 plus negative 16 over x minus 5. Now I'm clear to add the two fractions. When you add the fractions, only add what's in the numerator. So 5x minus 15 over x minus 5. Factor 5 times x minus 5 over x minus 5, and then reduce. X minus 5 divided by x minus 5 is 1, and so we're left with the 5 as an answer. Number 5, again we're subtracting fractions. We are going to have to multiply the left-hand side by x plus 3. And the right-hand side by x minus 1. So the first fraction, if I distribute the 3, I get 3x plus 9 over x minus 1 times x plus 3. Don't multiply the factors in the denominator, just the numerator. Minus, or I'm going to do this. I'm going to change that minus to a plus and make that a negative 2. So plus, distribute the negative 2, negative 2x plus 1. Again, same denominator. Now combine like terms, or add the fractions together, and we get 3x minus 2x is x. 9 plus 1 is 10. So x plus 10 over x minus 1 times x plus 3. And that is as simplified as we can get it. Number 6, we have a complex fraction. We have fractions inside of fractions. And there's a few ways to work through this. One, though, is to multiply the top and the bottom of the fraction by a common denominator. We have an x in the denominator. Well, when I mean denominator, I'm looking at, I'll circle them for you. These are your denominators, these 4, just looking at the smaller fractions. So a common denominator would be xy. So what I'm going to do is I'm going to multiply the top part of the larger fraction by xy and the bottom part by xy, because xy over xy is 1. We don't change the value by doing that. And when I do that, I end up with 3xy over x plus 4xy over y over 2xy over x minus 3xy over y. So we're just multiplying the xy with the numerators of all 4 fractions. Now all 4 fractions will reduce. So like 3xy over x, the x's cancel out and you have 3y. 4xy over y, the y's cancel out and you get 4x. 2xy over x, the x's cancel out, you get 2y. And 3xy over y, the y's cancel out and you get 3y. Sorry, 3x. There's nothing else that we can do. This is fully simplified. There is our answer. Alright, number 7, we're asked to add and simplify the 2 fractions. When you add fractions, you need a common denominator. Looking at these 2 denominators, they are almost the same, but not quite. One is x squared minus 9, the other one is 9 minus x squared. So I'm going to, well, just as a side note, a 9 minus x squared is the same thing as negative x squared minus 9. And if you don't see that, try distributing. If I put a negative in, I get negative x squared and a positive 9. If you think of that with just numbers, if I have 5 minus 2, that's the same thing as negative 2 minus 5. Try it out. 2 minus 5 is negative 3, negative 3 ends up being 3, and so on. It works with numbers, it works with variables. And it's a good trick to help you get a common denominator without having to do too much work. So what we're going to do here, we have 2x squared over x squared minus 9 plus, and we have x plus 15 over negative x squared minus 9. Denominators are almost the same. One's got a negative, the other one doesn't. Two options: we could multiply the left side by negative, or we can switch that negative, and that's what I'm going to do. I'm going to switch the negative. So we have 2x squared over x squared minus 9. Leave that one alone. And then I'm going to multiply the top and bottom of the second fraction by negative 1. So when I multiply the top part by negative 1 and the bottom part by negative 1. So now we have, distribute the negative, we have negative x minus 15 over x squared minus 9. Common denominators, we can go ahead and add the fractions. 2x squared minus x minus 15 over x squared minus 9. And now we're going to work on factoring. We're looking for the numerator, we're looking for two numbers that multiply to, so we're multiplying to negative 30 and add to negative 1. And so 6, or negative 6 and 5, right? So we have 2x squared minus x minus 15. We're just going to do a little factoring on the side here. And we split that up to 2x squared minus 6x plus 5x minus 15. Factor the left-hand side by factoring out a 2x. We're left with x minus 3. The right-hand side we factor out a 5. We're left with x minus 3. And then we factor out the x minus 3 and are left with the 2x plus 5. So back to our fraction. The top part factors to x minus 3 times 2x plus 5. The denominator is a difference of two squares that factors to x minus 3 times x plus 3. Notice x minus 3 divided by x minus 3 is 1. So we can reduce that fraction, and we're left with 2x plus 5 over x plus 3. Number 8, we're asked to simplify and then to state any excluded values. So in simplifying, notice the denominator is somewhat out of order. I'm going to put the x cubed term first, then the x squared term, and then the x term, just to rearrange this. So we get x squared minus 5x plus 6 over negative x cubed, negative 2x squared, and a positive 8x. And then we're going to begin factoring this. In the numerator, we're looking for two numbers that multiply to 6 and add to negative 5. So we can factor this to x minus 2 times x minus 3. In the denominator, notice we can divide all our terms by negative x. And we're left with positive x squared, positive 2x, negative 8. Try to factor further. So the numerator, we're done. We got x minus 2 and x minus 3. In the denominator, we have negative x times, can we find two numbers that multiply to negative 8 and add to positive 2? How about x plus 4 and x minus 2? And then we can go reduce the x minus 2's. We can divide by x minus 2 in the numerator and denominator. They cancel out. We get x minus 3 over negative x times x plus 4. So that is the simplified version of this fraction. When we look for excluded values are values that would make us divide by 0. We can't divide by 0, and so we got to decide what x can't be. When you look for excluded values, don't look at the simplified version. Look at the part right before you simplify it and just focus on the denominator. Just like we did last chapter when we found the x-intercepts of the polynomials, that's what we're doing. We're finding out what are the values of x here that would make each factor equal to 0. So the first one, negative x, gives us x equals 0. The second one, x plus 4, gives us x equals negative 4. And the third one gives us x equals positive 2. So those are the three numbers that x cannot be. Those we need to exclude, because if x were 0 or negative 4 or 2, then we'd end up dividing by 0, and you can't divide by 0. So these are my excluded values. Number 9. Place one or more expressions from the expressions option in each box to create an equation that is true for all values of x. So at first, let's just look at the equation on the left-hand side, the part that I'm highlighting. Okay, pretend the right side is not there, and just think, what would you do if none of this other stuff was here? You just had the part that was highlighted, and you were going to try to add those. When you add fractions, you need to get a common denominator. So I'm going to rewrite our fractions. So the first fraction is 7 over x minus 2. I'm going to put a little more space here. The second fraction is 4 over x squared. And the third fraction is 2 over x. We need a common denominator. If you look at the last two fractions, ignore the first fraction, just look at the last two fractions. If I multiply the bottom by x on the last fraction, then the last two fractions have an x squared in the denominator. So that's good. But then the first fraction has an x minus 2 in the denominator. So what I need in the first fraction is an x squared. What I need in the second fraction is an x minus 2. And then the third fraction also needs another x minus 2. Okay, so this is now going to set us up for our third step. Our third step goes to fill in the box, right? And notice, what is that common denominator? What do they all have? They have an x squared, and they have an x minus 2. And notice those are our choices. I picked the x squared, I picked the x minus 2 from our expressions options. Now you can use these options more than once. Now our first fraction has 7x squared, so we put the x squared next to 7. Second fraction has 4 times x minus 2, so I put the x minus 2 next to the 4. And the third fraction has an x and an x minus 2. And now I've filled out the box completely. We don't need to finish this, it's just getting this far, making sure we know what to plug in. Number 10. Here we're looking, we're going to state the following for the given rational function. We're looking for the vertical asymptote and for a horizontal asymptote if it has one. So on number 10, when we have a standard rational function, or the parent graph, you have a vertical asymptote on the x and y axis. So say here's our x and y axis. Say we had something like y equals -2 over x, which is the parent graph of this one. This has a vertical asymptote along the y-axis and a horizontal asymptote along the x-axis. And looks something like this. Okay. So what's happening here, this +4 is moving everything to the left 4. And then the -3 is moving everything down 3, including the asymptotes. So our vertical asymptote, before it's moved in the parent graph, the vertical asymptote is the equation x equals 0. And that's going to be moved left 4. So if we're moved left 4, then we're going to be at x equals -4. Our horizontal asymptote, and it does have one, is the equation y equals 0. That's going to be moved down 3, so then we're going to end up at y equals -3. Okay. Another way to look at this is, if you just go straight to the equation, that -3 is going to end up being your y-intercept. And then if you look at the +4, you do the opposite of +4, you get -4. That's going to be your vertical asymptote. So that's another way to go about that. Number 11. Given f of x equals 3 over the square root of x and g of x equals 3, solve the equation f of x equals g of x by graphing on the given coordinate plane, identify your graphical solution, and then solve the equation algebraically. Explain the relationship between your answers in part A and part B. Now for our graph of f of x equals 3 over the square root of x, I'm just going to make a couple points here. First of all, x can't be negative. You can't take the square root of a negative. Also, x can't be 0 because you can't divide by 0. So x can only be positive. So I'm going to get some points here that are easy to work with. If I plug in 1 for x into our function, we're going to get 3 divided by the square root of 1. 3 divided by the square root of 1 is 3. So 1, 3. If I put in, let's see, say 4. So I could take the square root of 4. I get 3 over the square root of 4, which is 3 over 2. 3 over 2 is 1.5. So I go right 4, 1, 2, 3, 4, up 1.5. My graph is not that big. And so what's going to happen is you're going to have this curve just in quadrant 1 that will, you'll never pass. We got this vertical asymptote at the y-axis. You also have this horizontal asymptote at the x-axis. So that's f of x. G of x is the function y equals 3. That's g of x. So part A says identify your graphical solution to where they both are equal at the same time. So it's where they're crossing. That's at 1, 4. Alright, now let's solve this algebraically. If I want f of x to equal g of x, I get 3 over the square root of x is equal to 3. I don't want a fraction, so I multiply both sides by the denominator, which is the square root of x. When I multiply the left side by the square root of x, and the right side by the square root of x, sorry, I said x, but I didn't write it. I'll try that again. These cancel out, and you end up with 3 is equal to 3 times the square root of x. Then we divide by 3, and we get 1 equals the square root of x. And then to solve, to get rid of the square root, we square both sides. So 1 squared is 1 times 1, which is 1. Square root of x squared is square root of x times the square root of x, which is x. And so x equals 1 is our answer. So explain the relationship between your answer in part A and part B. So part A gives you not only the x value of 1, but also gives you a y value, where part B is only giving you an x value. And so they have the same x value is what I'm going to state. Number 12, we have the function h of x is 1 over x minus 3 plus 1, and we're asked to sketch the graph. We can always make a table and plot some points that will work for us. And if we think here, we want to, it's a fraction, 1 over something, right? And so we get to pick what we want. Be nice to go 1 over 1. It's easy to divide 1 by 1, so what would x have to be to have 1 over 1? How about 4? So if x is 4, if I plug a 4 in, I get 4 minus 3 here. So I get 1 over 1 plus 1, which is 2. So I could plot that point, 4, 2. What would another easy number be to divide 1 by? How about negative 1? So if I have 2 minus 3, that would be a negative 1. So if I plug in a 2, I get 1 over negative 1, which is negative 1, plus that 1, so we end up with 2, 0. Okay, so there's another point we go through. Anything else seem easy to work with here? So, not without getting a fraction, right? Yeah, we could do a couple more, just for fun. What if we could divide by 2. So if I divide by 2, I'm going to get x is 5, right? So if we have 5 minus 3, we get 2. And so we get 1/2 plus 1, which is 1.5. So 5, 1.5, right there. And I could divide by negative 2. If I divide by negative 2, what would x have to be? A 1. So if we put 1 in for x, we're going to have 1 minus 3 in the denominator. And we end up with negative 1/2 plus 1, which is 0.5. So 1.5 careful, it's going by 2's here. Somewhere right there. Also 1.5, I guess I plotted that wrong. That should be I put it at 1. 1.5 is a little bit higher, but right there. So it's kind of what's going on here. It's hard to see. And so what we're definitely going to need, we don't so much need these points. You can get by graphing this without these points. I just want to put these on here to make our graphs a little more accurate. But what we definitely need is our vertical and horizontal asymptote. A couple problems ago we mentioned about the role of -3 here and the +1. That -3 moves us the whole graph to the right 3. From 0, 0, we go right 3, and then that +1 is up 1, right? So right 3, up 1. So this point I'm putting in blue is the center of our graph, and so that's where our two asymptotes are going to pass through that. Our vertical asymptote is right here at x equals 3, and our horizontal asymptote is right here at y equals 1. And then we can make a little more sense of our graph. This is where the top right part is. And second one, something looks off here. Let's see what's going on here. We plugged in a 2. When we plugged in 2, we got... Oh, I see what I did wrong. The 1.5, I plotted 1 -0.5. It should be 1 +0.5. So about right here. And which makes more sense because the second part is going to look like that. Okay. So there's our graph. Find the y-intercept. So where is this crossing the y-axis? Well, we could see it's between 0 and 1, but it's hard to see exactly where. So what we're going to do, and don't guess, don't pick what it looks like. We can always find a y-intercept by plugging in 0 for x and solving for y. So if I make x 0, I get y, which is my h of x, is 1 over 0 minus 3 plus 1. That is -1/3 plus 1. Going to get a common denominator. So -1/3 plus 3 over 3. And -1 plus 3 is 2. So this is 2/3. That's my y-intercept. So y equals 2/3. And if you look at the graph, that's believable. It's between 0 and 1. Looks a little closer to 1. So 2/3 seems reasonable. Find our x-intercept. Again, looking at the graph, I think we already found it. Right here at 2, 0. We know exactly where it's crossing. But let's just go through the work to confirm. Okay. To find our x-intercept, and to find any x-intercept, you set y equal to 0 and solve for x. So if we do that, we end up with 0 equals 1 over x minus 3 plus 1. Solving this, we need to subtract 1 from both sides. We get -1 equals 1 over x minus 3. Next, I want to get rid of my fraction, so I'm going to multiply both sides by x minus 3. And I get -1 times x minus 3, put in parentheses, equals 1. Sorry, that's not an equal sign, that's the next step. I'm going to distribute and get -x plus 3 equals 1. Subtract 3. And then x equals 2. And does that look like what we have in our graph? Yes, it does. We're going through 2. Found our x-intercept. Okay, the domain. I'm going to put this in interval notation, and notice we have two parts of our domain. Yeah, really, this the vertical asymptote x minus 3 is cutting our domain in half, because our graph goes from negative infinity on the left to positive infinity on the right, with a break in the graph. So you start at negative infinity, go up to where the graph breaks at 3 on the x-axis, union, start back up at 3, all the way to infinity. So that's saying everything except for 3. State the range. Well, it goes as far down as negative infinity, as far high as positive infinity, but it's got a break at y equals 1. So you go low to high, so negative infinity all the way up to our break in the graph at a height of 1. Union, start back up at height 1 and move all the way up to infinity. State the equations of the vertical asymptotes. We have one right here. We said it's x equals 3. Horizontal asymptote, we already wrote there 2 as y is 1. State the intervals on which the graph is increasing for part H and decreasing for part I. When we talked about graphs increasing or decreasing, you have to trace them from left to right. So if I trace this graph from left to right, you see it's dropping, so it's decreasing here. And then again, if I trace the other part from left to right, it's still decreasing. So this graph is decreasing everywhere, and it's increasing nowhere. So state the intervals on which it's increasing. When it says state the intervals, it's talking about what x values only, what part of the domain. And it's increasing over none of it. So we'll just say it does not increase. And where does it decrease? Well, because it decreases everywhere, I'm just going to copy down what we put for our domain, because those are the x values over which we're decreasing. State the interval for which our graph is less than 0. Okay, less than 0 means below the x-axis. So we are below the x-axis right here that I'm highlighting green. But when we state it, don't state the height, only state the x value. So the x-axis, just a little part of the x-axis is covered there. Okay, and it's got to be less than, not equal. So we start at our x-intercept, that's where that green part starts at 2, and it ends at at 3. And I'm going to use parentheses for both, because we don't want to include 2, because that's when it's equal to 0. It's not below the graph, it's actually on the x-axis. It's an x-intercept. And I don't want to include 3 because there is no graph there. That's where our vertical asymptote is. State the intervals on which the graph of H is greater than 0. That's everything else. So from negative infinity, we're talking about x values, all the way up to the 2. Okay, I'll highlight it in blue here. So I'm going from negative infinity all the way up to right there. And I don't want to include the 2 because 2's at 0. I want to go above. And then it picks back up here and goes all the way to infinity. So it picks up at 3 and goes to infinity. Only x values here, no y values. Number 13. The width of a tree ring decreases with its ring number x. The function w of x equals 1 over the square root of x. Shown in the figure, sorry. So it's already graphed for us, and it models the ring width. Okay, so here we have some context. The width of a tree ring decreases with its ring number x. So I'm going to write ring number on the x-axis. And the function w, that's our y value, w represents what? The ring width. So you get the ring number, and this is the ring width. That's our y-axis, or w. And we're talking about trees. So explain why the graph of W is only in the first quadrant, first using mathematical evidence. When we talk about mathematical evidence, we're not talking about context. So don't use the word ring, ring width. Go straight to that equation. So W of x equals 1 over square root of x. Why can it only be in the first quadrant? Well, first quadrant means in the first quadrant, all your x values are bigger than 0, and all your y values are bigger than 0. So it's really asking, why is x bigger than 0, and why is y bigger than 0? So my answer is, x is bigger than 0 for two reasons. Since we can't take the square root of a negative, if x was a negative, we'd have to take the square root of a negative number. So since number one reason, we cannot take the square root of a negative number. Okay. And the second reason, so that's why it's not negative, but why isn't it 0? Well, if x was 0, then we would be dividing by 0. If you can't plug a 0 in for that equation. And 2, we cannot divide by 0. So that's why x is positive. Why is y positive? Well, since x is positive, we're only plugging in positive numbers. And so if you look at our equation, so our y value is going to be positive since y is equal to 1 over the square root of of x, and x is a positive number. And if you have 1 divided by the square root of a positive number, that's going to equal a positive number. So we are always going to get positive y values. So if you're always working with positive x values and positive y values, then you're always going to be in the first quadrant. So there's our mathematical explanation. Number 14, we're given two functions, f of x and g of x, and we're asked to solve f of x equals algebraically. So we're going to start by setting, so f of x equals g of x, so f of x is 5 over x plus 2, and set that equal to 3 over x, which is g. Whenever you have a fraction, no matter what kind of fraction it is, and you're working with an equation, you can get rid of that fraction by multiplying by denominators. So let's look at the first fraction, the 5 over x plus 2. If I multiply the top part of the fraction by x plus 2 and do the same thing to the right hand side, multiply that side by x plus 2. I'm allowed to do that because I have an equal sign, and you're allowed to multiply the same amount to both sides. What that does for me is it allows me to cancel out the x plus 2's and end up getting 5 is equal to 3 times x plus 2 over x. Now I just have one fraction left. To get rid of that fraction, multiply both sides by that denominator. So I multiply the right side by x and the left side by x. That allows me to cancel out the x's, and now I have 5x is equal to 3x, 3 times x plus 2. No more fractions. I'm going to distribute the 3 times the x and the 2, and you get 5x is equal to 3x plus 6. Subtract the 3x, and divide by 2 and get x is 3. Okay. Go back. You always want to go back and check to make sure that when you plug in x equals 3, that doesn't cause you to divide by 0. What I mean is, in our first fraction, the 5 over x plus 2, if I make x 3 there, I get 5 over 5. That's fine. I can divide by 5. If I plug in 5 for x in my second fraction, I get 3 over 3, and that's fine as well. We just need to make sure when we plug in x, it doesn't cause us to divide by 0. Number 15. I have my equations. I'm going to focus on the first fraction first. To get rid of that fraction, I need to multiply both sides by x plus 1. And that allows me to cancel out the x plus 1's on the left-hand side. So now I have negative 3 is equal to 4 times x plus 1 over x minus 1. Now I focus on the second fraction. I want to get rid of the x minus 1, so I'm going to multiply both sides by x minus 1. And that allows me to cancel out the x minus 1's. So now I have negative 3 times x minus 1 is equal to 4 times x plus 1. Distribute. And then solve. So I'm going to add 3x to both sides of the equation. Subtract 4. Divide by 7. Number 16. If you have a fraction and if the denominator is factorable, then factor it. Here our denominators x squared minus 8. Nothing, it's not a difference of 2 squares, so I'm going to leave it as is. So I'm going to first I'm going to get rid of the fraction on the right. So I'm going to multiply the right side by x and the left side by x. That allows me to cancel out the x's on the right hand side, and I get x squared over x squared minus 8 equals 2. Can I cancel out the x squareds? Your answer should be no, because that the x squared in the denominator is connected with that negative 8. The only way to disconnect that is to factor an x squared out, and you can't factor an x squared out because the 8 doesn't contain one. So no, we cannot cancel out the x squareds. But we can get rid of that fraction by multiplying the top by x squared minus 8 on both sides. That allows us to cancel out the x squared minus 8. And now we're left with x squared equals 2 times x squared minus 8. Distribute the 2. And then continue working through this. I'm going to subtract 2x from both sides and get negative x squared equals negative 8. Then divide by negative 1 and get x squared equals positive 8. going to take the square root of both sides. The square root of x squared is the absolute value of x, because x could be positive or negative. And so then whenever you have the absolute value is equal to a number, you split it up into two cases. But remember, the square root of 8 is the square root of 4 times 2. Square root of 4 is 2, and so we get 2 radical 2. So we're going to split this up to x equals positive 2 radical 2, or x equals negative 2 radical 2. Now there's an issue on number 16, and let me point this out. Our first fraction, before we even started the problem, was x over x squared minus 8. And we solved and got x equals 2 root 2, or negative 2 root 2, right? But if you look back, I'm going to highlight it for you. Notice what x squared is equal to. We have x squared is equal to 8. That's an issue, because if we replace x squared with 8, we're going to get 8 minus 8 in the denominator, which is 0, which means we'll be dividing by 0. So we can't accept any of our answers. We have to throw them out and say that there's no solution to this problem. So it's important to always go back to your original fractions and say, hey, if I plug in those values for x, will I be dividing by 0? If so, you have to throw them out. So in 16 there was no solution. In 15 there was one solution. In 14 they didn't ask how many solutions. Let's take a look at 17. 17, I'm going to start by getting rid of my fraction on my right. I'm going to multiply both sides by 3. 3's cancel out, and you end up with 3 times x minus 4 over x plus 3 is equal to x. I want to get rid of my first fraction. I'm going to multiply by x plus 3 on both sides. That allows me to cancel out that fraction, and we now have 3 times x minus 4 is equal to x times x squared, which is x squared, and x times 3 is 3x. Keep going, we get 3x minus 12 equals x squared plus 3x. If you subtract 3x from both sides, you end up with x squared equals negative 12. And then you end up trying to solve for x. You take the square root of x, but you hopefully recognize that there is an issue here. The square root of a negative number is imaginary. And when we're talking about how many solutions there are, we're focused on real numbers. So let me add that. So how many real solutions are there? And so in terms of solving for real solutions, there are none. We can keep on solving this. We'll get our imaginary solutions. We get the absolute value of x is equal to negative comes out, we get I. 12 is 4 times 3, and we can take the square root of 4, so this is 2I square root of 3. That's the absolute value of x, so when you split up the two cases, x can be positive 2I root 3, or x can be negative 2I root 3. So we have two solutions. But no real solutions. Number 18. Okay, now we have three fractions. Two of the fractions have the same denominator though. Two of them have the denominator of x minus 1. So I'm going to multiply all three fractions by x minus 1. That allows me to cancel out the denominators and get rid of two fractions. So I'm left with x minus 2 times x minus 1 over x, which is equal to 1. Got one more fraction, multiply by that denominator, which is x. So I'm going to multiply this by x here, multiply this by x, and this by x, and that allows me to cancel out my second, or get rid of my second fraction, and I end up with x squared minus, I'm going to distribute negative 2 times x is negative 2x, and negative 2 times negative 1 is positive 2, equals x. Subtract x from both sides, because this is quadratic. You get x squared minus 3x plus 2 equals 0. And try to solve for x. In this case, I'm going to try to factor. I'm looking for two numbers that multiply to 2 and add to negative 3. Negative 2 and negative 1. So this factors to x minus 2 and x minus 1. And solving this, you end up with x minus 2, 0, giving you x equals 2. And if x minus 1 is 0, you get x equals 1. Let's go back to our original fractions and make sure these are acceptable. Just focus on the denominators. So if my denominator is x minus 1 and I can't divide by 0, then I can't have x equaling 1. Well, that means I need to throw out that fraction, or that answer, x equals 1. If the denominator is x, then x can't be 0. I don't have that as a solution, and again, can't have it to be 1. So I do have one answer, which is x equals 2. The other answer we had to throw out, we call it an extraneous solution, because if we plugged it in, it would cause us to divide by 0. I'm going to try to factor, first of all, the x squared minus 6x plus 8. Looking for two numbers that multiply to 8 and add to negative 6. Negative 2 and negative 4. So we can ignore that now. Change it to the x minus 2, x minus 4. And notice, well, then we start getting rid of our fractions. I want to get rid of the first fraction by multiplying by x minus 2. Can cancel out my x minus 2's. And I'm left with 4 plus 8 over x minus 4 is equal to x minus 2. Next, I want to get rid of my remaining fraction by multiplying everything by x minus 4. Allows me to cancel out the x minus 4's in the fraction. And now we have 4 times x and 4 times negative 4, which is 4x minus 16. We have an 8, and that's equal to x times x times negative 4, negative 2 times x, and negative 2 times negative 4. Clean this up a little bit. Left side is 4x minus 8. Right side is x squared minus 6x plus 8. I'm going to make the one side equal to 0. So I'm going to subtract 4x. And then add 8. And now try to factor. We're looking for two numbers that multiply to 16 and add to negative 10. But negative 8 and negative 2. So the first one gives us x equals positive 8. The second one gives us x equals positive 2. Let's make sure we can have those as answers, or see if they're extraneous solutions. Well, our first fraction has a denominator of x minus 2, which means our x cannot equal 2. So I've got to throw that out. Second denominator has an x minus 2, so x can't be 2, and x can't be 4, so 8 is acceptable. We'll keep that one. Number 20, we have a word problem here. We have a group of friends that decide to evenly divide $72, the cost of watching a premier boxing match on a pay-per-view TV. Initially, there are X friends, but then 3 friends decide not to watch the boxing match and spend their money to see Star Wars Episode 23, The Never-Ending Force, at the movie theater instead. This causes each remaining friend to have to pay $2 more. So create an equation that represents the situation and can be used to solve for x. Okay, so x represents the number of friends. And costs $72 to watch the premier boxing match. Okay, so if we had X friends and you divided that 70 to $2 up between everybody would pay $72 divided by X. So this is the this represents the cost initially, or the cost with X friends. But then what happens is 3 friends decide not to watch, and so now it still costs $72 to watch, but now there's only 3 friends, so there's 3 friends less. So there was X, now there's X minus 3 friends, so now this is the cost with X minus 3 people. So my question to you is, which cost is more? Did it cost more when you had X friends, or does it cost more when you have less friends? And hopefully you realize that, okay, if there's less people splitting up $72, they're going to have to make up for the difference. They're going to have to pay more money. Okay. So we know that 72 over x minus 3 is more than 72 over x. How much more? It says $2 more. Okay. So if I want to set these things equal, well, 72 over x minus 3, if I want to set that equal to 72 over x, well, they're not equal. The first fraction is more than the second fraction. How much more? $2 more. So I'm going to add 2 to the second fraction, and now they're equal. So use that equation to solve for x. So 72 over x minus 3 is equal to 72 over x plus 2. To get rid of the first fraction, I need to multiply by everything by x minus 3. Don't forget the 2. That allows me to cross out my x minus 3's. To get rid of the second fraction, we're going to multiply everything by x. And that allows me to get rid of the x's in the second fraction. Clean this up, see what we're left with. We have a 72x is equal to 72 times x minus 3 plus 2 times x minus 3 times x. Keep working through this. 72x is 72x minus 72 times 3. It should be 216. And then 2x times 2 times x minus 3 is going to be 2x minus 6. I still need to multiply it by x. Actually, notice we have two 72x's. So let's subtract both sides by 72x, and we end up with 0 equals, these cancel out, negative 216 plus multiply 2x times x, so 2x squared, and minus 6x. I'm going to put things in order. So the 2x squared first, the negative 6x second, the negative 216 third. Everything's divisible by 2. Divide everything by 2. And now we're factoring. Try to factor. Can we come up with two numbers that multiply to 108 and add to negative 3? So start thinking of what are my factors of 108. So 108 is even, so 2 times something, right? So 2 times 54. 54 is even, so 2 times 27. 27 is 3 times 9. 9 is 3 times 3. So 108 is 2 times 2 times 3 times 3 times 3. That's the prime factorization, and we're trying to figure out, well, what two numbers could we multiply together to get 108? Well, we could do 2 times 2 times 3 and 3 times 3. That would be Well, 2 times 2 times 3 is 12. And 3 times 3 is 9. 12. So we know 12 times 9 is 108. Can we make a negative 3 out of that? Not quite. If they're both positive. Oh, I'm wrong. It should be a negative 108. So we can make this work. Negative 12 and a positive 9. So now we get x minus 12 and x plus 9. Giving us x is 12 and x is negative 9. So should we take both those as our answer? Well, what did x represent? X represented the number of friends. Can I have 12 friends? Yes. Can I have negative 9 friends? No. So throw out that negative 9. It doesn't make sense in the context of this problem. Keep the 12. Number 21. Aubrey can wash all the windows of a retail store in 6 hours. Maxwell can wash all the windows of the same retail store in 9 hours. So it takes Maxwell a little bit longer. Write an equation that can be used to find the time in hours it would take Aubrey and Maxwell to wash all the store, all the windows together. Okay. Well, so T is how long they're working. Okay. So if Aubrey works T hours, she's completed, I'm going to use a capital T. She's completed T over, it takes her 6 hours, so T over 6, that's the amount of the job she's completed. So for example, if she's worked 1 hour, plug in 1 for T, and she's completed 1/6 of the job. If she's worked 3 hours, plug in 3 for T, and she's worked 3 over 6. So 3 over 6 is half. She's completed half her job. Once you plug in 6, if she works 6 hours, she's completed the whole job. And so 1 represents the whole job. If you think of it as a percent, 1 is 100%. Now, Maxwell is also working the same amount of time. So he's working T hours, but he's working at a different rate. It's taking him 9 hours to complete the whole job. So the fraction of completion is going to be T over 9 for him. And they're working together, so I'm going to add these two. And we want to know how long it takes for them to complete the whole job. 1's representing 100% of the work being done. So there's our equation. And I'm going to get rid of my first fraction by multiplying everything by 6. That allows me to cancel out the 6 in the first fraction. And then multiplying everything by 9. Allows me to cancel out the 9 in the second fraction. And so we're left with 9t plus 6t is equal to 6 times 9, which is 54. 9t plus 6t is 15. Divide by 15, and the time is 54 divided by 15, which we could reduce. You could divide both by 3. 3 goes into 54 18 times. 3 goes into 15 5 times. If we change this to a decimal, we get 3.6. We're talking hours here. So a bit more than 3.5 hours working together at their rate will complete it for them. And that's it for the review. Good luck on the test.